Okay. All right. Yeah. So, and then I'm going to give you some examples, but as part of a broader story about some of the methodologies that I have developed and how they have interacted or how they have been synergistic with the kind of philosophy I follow in scientific research. And then, thank you. Yeah, and then focus on impactful science and policy. Because it's not only conducting transdisciplinary research, but taking it all the way to the policy or towards societal impact. And I'm going to give one example as part of the committee from the National Academy of Sciences that I have been a part of recently. And then finally, I'm going to talk about the synergic impact of climate change, and actually there is a typo here, air pollution. And I'll try to tell you a little bit about what I'm currently involved in, both in terms of methodologic research, but also my move towards climate science and climate data science as well. So this is kind of roughly the outline. So my general approach to transdisciplinary research is, first, of course, as a biostatistician, my primary focus is on methods development, right? So that is the mainstay of the stuff that I do. But then I also believe strongly in meaningful immersion in team science. So I don't see myself as someone who just takes ideas, spits out equations and p-values, and then step back. But I actually involve in the team science itself in a meaningful way so that it actually informs what I do in terms of methods development. So this actually allows me and allows the team to do many things. One is, as a statistician, I believe that I have a unique quantitative input into the team science. And this is both in terms of informing the design of meaningful studies and also shaping the modeling framework, or taking a conceptual framework that a domain scientist actually comes up with and translating it into mathematical formulation and try to design studies that would answer the scientific questions of interest. Right? And then my own research is not only at the domestic scale, but global scale. And as Dr. Collins said, I myself am global by design, so I cannot help but be global in my research as well. And you will see, hear some of that. And then, of course, one thing that has been the mainstay of my own research is this productive loop in terms of methods development and domain science research. All my ideas, almost every paper that I have written in statistical methodology has been inspired by what I have learned as a gap in analyzing data effectively. Right? And then you go ahead and develop that method, and you try to influence your colleagues to, apply for grants that use these new methods. So there is this kind of, very nice feedback loop that has defined my career for the last 30 years. And I'm going to tell you a little bit about that as I go through my story. And then, of course, in the last, few years and decade, maybe even more, this delusion, of big data, but also the emergence of data science as a discipline, still evolving, still in fusion, has produced both challenge and opportunity, right? So we have a lot of data. If we use them wisely, of course, we can inform science in a very meaningful way. But if you don't know how to use them, you're basically being buried and inundated by a lot of information. And the signal may be buried in the huge mass of data unless we have the right tools. So this has been actually also a part of my focus and also my group's focus, at Columbia and when I was at ESC. And of course, emphasis on ethical and responsible science is extremely important. And just because we have huge amount of data, huge volume of data, it doesn't mean that we're getting consistently similar or comparable results or data from all sectors of the population or society. And sometimes we actually get this sense, false sense of comfort that we have a lot of data, so we can answer every question imaginable. But there is huge disparity in terms of availability of data. There is huge disparity in terms of quality of data. And if we use the right tools in statistics, we may discount information that comes from segments of population. If we don't use the right tools, we may be using messy data, and we basically mess up the answers that we get to questions because we don't have the right tools, right? So this is kind of a double-edged sword in a way. And ethics and responsible science is definitely at the center of everything, should be at the center of everything that we do, especially when it comes to data science, machine learning, and artificial intelligence. And of course, I believe in having active role on policy translation. We can publish the most sophisticated statistical methods. We can publish the most highly cited scientific publication in Lancet, New England Journal of Medicine. You can publish in Annals, Biometrics for methods. But if they stay there on the shelves, then we haven't done our job. So that policy translation is extremely important. And I truly believe in that. And it has been part of my practice as well. All right, so that's the philosophy. Now, let me tell you a little bit about the motivating example. One example that, from a data set that I have been involved in, or a studies that I have been involved in since 1997, actually, since I moved to California. This is the Southern California Children's Health Study. Okay, so the whole point of this study was, when it comes to health impacts of air pollution, there was a lot known about what we call acute effects of air pollution on health. But it was very difficult because it's expensive to answer questions, in children or in any segment of society, does long-term exposure to air pollution impact health, right? So to do that, you have to conduct longitudinal studies, and they're very expensive. So the California Air Resources Board was actually generous enough to give ESC about $20 million in order to recruit thousands of children, but in a way that actually we can collect both the exposure, but also the health impacts on children, follow them enough so that he can tell whether growing in a polluted environment impacts health, right? So that was actually the whole premise of this study. And it followed a multi-level design because you want to know where people are living, but you want to have contrast across, communities. So in Southern California, going a little bit to the north because we needed to have some clean sites because Los Angeles Basin itself is very polluted. So we selected like 12 communities that had very different pollution profiles, and hundreds of children were recruited from these, communities, and then followed over time, measured lung function, many other, respiratory health and other health outcomes, along with socio-demographic variables, in order to see whether living or growing up in a polluted environment impacts your growth of lung function or overall respiratory health compared to children that grew up in relatively cleaner society, community. Of course, there are many nuances that I'll come to later on because you can live in a very clean community, but if your house is next door to the school bus that passes every day and you have diesel fuel, living in a clean community actually doesn't help you, right? So there is that spatial and temporal resolution over time and over space that you really have to tease apart, and you have to be able to identify where the effect is coming from. And you need to have the right design in order to be able to answer that, okay? So original purpose was to, for chronic impact of air pollution. All told, over 20-year period, close to 12,000 children were actually recruited over 5 cohorts in different time points. And then, of course, many things were done. As I'll tell you just, in a moment, there were many complexities in the data because as children grow, we have the growth spurt, and height is changing in a very nonlinear and complex way. And how do you capture that, physiologic, nonlinearity, but how do you relate that to the exposure? And how do you tease apart what we call biologically meaningful aspects of the curve, in terms of, health? And of course, genomics, genetics, epigenetics, many, really rich, data that, after so many iterations, the investment on this study has been like more than $100 million, probably easily. And it has taken a life of its own. So ever expanding and evolving research agenda, multiple outcomes, and, and other branch, studies that were never part of, the original study design. Like for instance, cardiovascular, neurocognitive, tobacco products, and also obesity, childhood obesity in relation to built environment and so on and so forth. I'm not going to tell you about all those today, but each one of these actually has generated ideas for statistical methods development that also fed into that, feedback loop that I told you about. But I'm going to zero in on some aspects of this just in the interest of time. So the multi-level design, essentially the design should allow for the multifactorial etiology. It should emphasize, impact across multiple levels. Temporal, you could have repeated within subject measurements to characterize growth curves. So what is the impact on time? Spatial, you could have, enough number of neighborhoods, schools, communities. How do you tease apart the spatial-temporal, impacts? And of course, a model should allow for proper inference at different levels in a way that he can actually make them orthogonal enough to each other, that he can tell, this effect is happening at this level, not at this level, in a way that's actually independent from each other. And from statistical point of view, you have what we call these cross-level effects, cross-level bias, or cross-level interactions that could actually mess up things unless you, systematize them properly. Okay, so what we did was, and the design actually was given in a paper in 1994 before I joined BSc actually, because it's a very complex, design. So what we did was actually, once data was collected and epidemiology papers were starting to be written, we actually wrote a paper on statistical science, basically talking about what are the many issues that we have to grapple with if we're going to make sense of the rich data that's going to be collected as part of this study. And this was actually a very, almost kind of a roadmap in terms of the many research projects that we conducted later on, both from domain area, but also from methodology point of view. How do we handle the nonlinear growth trajectory? How do we handle what we call ecologic bias? Because the design has ecologic and non-ecologic components. How do we handle correlated multiple outcomes? Because you could have like 5 different lung function measurements on the same child. You could have, asthma information, bronchitis information, and so on. Because they are coming from the same subject, they are interrelated. They are not independent of each other. But do you do inference one at a time, or do you try to get at the underlying respiratory, etiology? And how do you synthesize evidence across multiple outcomes? Outcome is classification. Like, for instance, we are getting information about asthma, but we're getting it from questionnaires. So you ask a child 1 year, they say, yes, a doctor has told me I had asthma. Next year they come and they say, no, I've never heard that I had asthma. So which one is the truth, right? Do you ignore that information? Or do you account for that using proper statistical methodology? Measurement error is a big problem in exposure and outcome. Multi-pollutant problem or multicollinearity is a huge problem. And we proposed a Bayesian model averaging approach, but of course, the field has really advanced much more. Exposure metrics. What is the right exposure metric? Is it the cumulative exposure? Is it the exposure a day before or a year before? Or is it cumulative across time? And if you try to account the progressive impact, how do you capture that without messing up the modeling? Because there will be multicollinearity. So this paper actually really lays out these whole issues and basically gave us a roadmap. It was a discussed paper that actually had input from many prominent scientists in the many fields. So again, I will have some slides with the questions, but I'll try to focus on the concepts because I know this is a mixed audience. So I don't want to turn this into a statistical talk, right? So if you want me, I can, but I'm sure that's not the purpose. So basically just a cartoon version of this 3-level model. Essentially what you're doing here is in level 1, you're trying to make comparison between times within subjects, right? So just to focus it, I don't know whether the pointer works. Yeah. So here you have an outcome. Think of this as lung function measurement in community C, subject I, and time K. Okay. And then you have covariates that are at the time level, and you have this is the first air pollution or exposure value, and then you have of course the error, and then from this you basically tease out the adjusted level. If you center age, then this could be lung function at certain age adjusted, and this could be the rate of growth assuming linearity, right? And then you go to level 2, you have between subject within community comparison. In level 3, you have a between community comparison, right? So in our case, we had 12 communities, and therefore the level 3 is basically at the end of the day, accounting for everything that's happening at the many levels. The fundamental question of the study was, does living in a polluted environment compromise your respiratory health, for instance, right? But you don't want to do it just starting from the third one, which would be purely ecologic and throwing away a lot of information. but you would like to do it by accounting and adjusting for everything that's happening over time within communities, and then finally the between communities. And the reason that we have this, subtractions, in Beta 1 and Beta 2 and Beta 3 is essentially because you can think of Beta 1 and Beta 2 and Beta 3 orthogonal effects, where this is, between time within subject, between subject within community, between community. And then you can either test whether these are, the same, or this could be different, or one level could dominate the other. So you actually have the ability to answer questions in a very orthogonal way. And this is just the cartoon in terms of what you're taking from level 1 to level 2 or level 2 to level 3 to focus on either growth trajectory or growth slope or the level of lung function, let's say at age 18, if you center age at age 18, for instance. So remember, I told you that when children are growing, and these children were recruited when they were 9 or 10 years old, and we followed them all the way to high school graduation, there is that magical growth spurt that's happening in between, when they are growing. You cannot ignore that, because lung function is a direct result of the physiologic growth of height, but it has a very very interesting physiological feature, which is well known, that it's depend like the effect of age, height, and lung function they are interrelated, right? There is actually a very well defined, structure where the lung function grows kind of lags by 6 months from height, and you really need to capture that, right? So you have to modify this three-way, model in order to be able to do that. So what we have done is essentially what was linear, A and B. A is a level and B is a slope, or intercept and slope. Basically, we changed this into nonlinear function. And what we used here was actually things like smoothing splines or piecewise polynomials in order to capture the nonlinearity, right? So you're essentially acknowledging that there is a nonlinear growth, and then there is also this very interesting interaction with height as well that's happening. So you do this, and we come up with what we call time varying coefficient model, well defined in the generalized additive model literature. And then, of course, because you have very limited number of observations per subject, we're getting only one measurement per year over 8-year period. If you want to really characterize the growth trajectory per subject, you don't have enough data. But you can borrow strings from many subjects living within homogenized subset, and then you can have a very rich random effect structure in order to allow for that heterogeneity between subjects. But you borrow strings from people to basically fill in the data. So that's essentially what the arrow is all about. Now, so this is basically what the physiology is. This is actually the conceptual driver of the work. Is essentially, you have someone who is either starting low for lung trajectory, and then they're growing, but either they can grow naturally, or they could have some assault that actually compromise their trajectory. So this is age, from 0 all the way to old age, and this is kind of one of the lung functions in % of predicted maximally attained value. So 100% is good. So the higher the plateau, the better. But essentially, someone could follow different trajectories, like the green, which is the best. Then you have the yellow, and then you have the red, and then you have the black. So if like 60% is a magical point where you get COPD and things like that, then there could be premature deaths as people grow. But for our data, we're only focusing in the age between 9 and 18, essentially, and we are trying to capture this. So essentially, by using smoothing splines, we basically, model the data. Of course, the girls are, maturing earlier, and therefore the trajectory is different from the ones for the boys. So we capture that through using generalized additive models in a mixed effects format. Okay. So the question now is, when you have linear growth, then you can basically take the slope or the intercept. But when you have nonlinear trajectory, what aspect of that curve is going to be related to air pollution? Okay. So essentially, trajectories are nonlinear, rates are changing with age. How can we perform air pollution analysis? So we try to identify what are the most important parameters. Growth over the childhood period could be one, which is very simple because it's only the difference. Whatever you do to model, you can just take the difference and then do it simply. Or maximum rate of growth, which is complicated, what we call nonlinear functional, or maximum attained lung function level, right? Where the people are ending towards the end. So these last two are actually problematic because they don't have closed form variance estimation or uncertainty estimation. So that actually, part of one of the papers that we wrote in biostatistics in 2008. Essentially, we try to use functional-based flexible multi-level modeling using Bayesian framework in order to model the growth trajectory, but then to capture the velocity of the curve and then attach the velocity or the attained level with the air pollution values. Okay? So this is basically what I just said, and I'll skip it. But essentially, what the question is, how do we estimate uncertainty or variance estimate for nonlinear functionals for this maximum rate of growth or attained lung function? So we use what we call this Gibbs sampling, a Bayesian technique in order to be able to do that. Again, too many symbols here, but essentially the same thing that I said here before. Essentially, what you're doing is you're capturing the nonlinearity through this expanded, what we call expanded basis function. So this is a one for age, this is a one for age and height, but the rest is basically kind of bookkeeping. So I'm not going to go into a lot of detail. We consolidate, and then we try to set it up in a Bayesian setup, which again, I'm not gonna go to details, but anyone interested, we can follow up later on, especially when I'm having my discussion with the biostat group, we can have fun later this afternoon. But for this purpose, all I wanna say is basically that, the setup actually is well characterized and mostly standard actually, so well-established methods, but it's allowing us to do the right thing in terms of characterizing what the uncertainty estimates are. So essentially, this is a modeling paradigm. You try to model the non-linearity, and then you try to capture the uncertainty estimate for what we care about, and then it takes that in a multi-level model in order to basically do your inference. So I'll cut to the chase without going into a lot of detail. After all that equation, essentially, this is what you end up with. So what happens here is, this is MMAF, one of the lung function measures for flow rate. And we model girls and boys separately because the trajectory is different. So essentially, the solid curve is the growth trajectory. So for girls, a lot of them have actually already matured. So you don't have that inflection point that you have for boys here, because boys are maturing a little bit later during the study period. And then those broken lines that you have around the curve is essentially what we are using the Gibbs sampling in order to characterize the uncertainty around it, more kind of confidence bands around the curves. But what we do is actually, and this is one of the innovations here in this work, is basically, you see here, basically what you have done is, through the Bayesian modeling, you're trying to basically characterize the velocity. So basically, you're taking the rate of change of this curve, which looks like this, and the rate of change of this curve, which looks like this. So here is basically what I'm calling the maximum rate of growth. But this histogram here gives you the variance estimate, which you cannot do inference without, basically, right? So doing that, this is the bottom line. After all that work, this is a punchline of the paper, basically, right? So in other papers, we have shown that change in lung function over the growth period is associated with lung function, with air pollution, and living in a polluted environment basically compromise your lung growth. What you have seen here is basically we are zeroing in the maximum rate of growth, and what this table shows in a nutshell is basically that most of the damage is happening when children are growing the most. So if a child grows the most in a polluted environment, then their lung is going to be compromised, and it will be setting them up for a very compromised life, later on, both in terms of quality of life or even premature death. So that's the punchline, right? So almost like 60% of something of the damage is happening during that period where they are growing the most. So this is basically what I was trying to say. This idea, the idea came from the problem itself, and we had to come up with a new method, and that method actually allowed us to answer a very important scientific question. So that's kind of the feedback loop that I was talking about, just as an example. Okay, this is essentially this part of the same story. I don't know how am I doing with time, because sometimes I get carried away. If you have only 1 hour, yeah. So I think, we need to speed up. So I'll give you a brief example here as another, remember I told you we had outcome misclassification as one of the issues that we have to deal with, and especially with asthma information. When, the outcome we know is misclassified, we cannot trust it, right? So we have to do something about it, right? So how do we account for the potential misclassification from the information we have, but reach a valid conclusion from our data without misleading the audience about what's happening? So essentially, this was kind of sub-studies that actually basically showed that there was misclassification. That's all I need to say about this without going into a lot of detail. So asthma information is coming from questionnaire, inconsistent from year to year. We need to account for potential misclassification. And this is because there is a known bias if you ignore, let's say, you just use logistic regression because you have asthma, no asthma, and you ignore that people are not telling you the same thing consistently from year to year, then you will get biased results. So your conclusion is going to be wrong. So how do we correct that? So we came up with something called as the mixed hidden Markov model as a tool in order to come up with a new approach. Okay, so this is probably going to be the last example I show from this. There is one more complicated one that I'll just breeze by in the interest of time, but you get the point. I think the idea is identify a very important problem, solve it mathematically, come up with the right method, and then solve the scientific question. And and then of course using that apply for other studies so that you can advance science. I'm not going to go into a lot of detail about this. Basically, this is details about the mixed hidden Markov model, essentially what we have is we don't know the truth. The truth is hidden, right? What we call latent state, right? But what we are seeing is manifestations, potentially imperfect manifestations of the truth is what we are getting. So our observed data is measured with potential misclassification, but the truth is something that we don't know, but something that we want to do inference on. Not the faulty data, but the true data is what we want to make inference on. That's the whole point, basically. So again, some equations here just to set notation. Here, basically, you have different states for observed subject I at time j. In this case, it's setting up for multiple states. But to simplify ours, let's think asthma, no asthma. So only two states, basically, right? But this is kind of essentially setting it up for any problem. Like, for instance, you can think of no asthma, asthma, and in between, you can have many variations of wheezing, for instance, in the continuum of the process towards development of asthma. We're also assuming that asthma is an absorbing state. In other words, once a person has asthma, then they don't get out of it, even though they can outgrow it, as we know. But in terms of physician diagnosis, if you had asthma at some point, the story stays the same, even if you don't have symptoms later on, right? So for our purpose, we are assuming it's an absorbing state. So, because it's physician diagnosis. And all the other stuff is essentially to account. Remember, we have a multi-level design. We have multiple communities. We have multiple subjects. We have observations over time. So we have this mixed effect set up in order to account for all that dependence within subject, within community, and across time. Okay? So that's essentially what all these equations are or symbols are trying to do. So this cartoon is actually probably the most important one. Again, this is a paper published in 2014. So essentially what this is doing is you have, this circle is unobserved state and the rectangle is observed state. So essentially here you have the real state of asthma for, subject I time 1. But what you're observing is this potentially misclassified or faulty one. And the real one is being impacted by covariates, right? By variables. But the misclassified one also is being affected by covariates. And then time is marching. So you have time 1, time 2, up to time ni, because each subject could have different numbers of observations as a follow-up. So that's essentially the setup, the cartoon setup. And then you have this, one part, which is the true that we are going after. And this is basically the overtime one. And this is essentially the relationship between what is the truth and what is observed, right? So those are the things that you're going after. And then, of course, because we have a multi-level design, you have to allow for those dependency in the data, which is what I mean by complex data structures. So flexibility in terms of modeling multi-level cluster effects, we capture heterogeneity among subjects, we allow for differential misclassification, and at the end of the day, once you set it up, it's actually very easy to implement this because you're basically bringing it back to familiar modeling approach, even though you have set it up properly. The key is actually in setting it up properly. Okay. Again, I'm not going to go into a lot of detail about this. So what we're calling initial probability is what's happening at baseline. What's the prevalence probability? Okay, that's one. And then you have certain parameters you pick, and then we have the transition probability. What's happening over time? So from time 1 to time 2, are you moving from one state to the other, and with what probability? Like from asthma to no asthma, or from no asthma to asthma, and so on and so forth. Again, I'm not going to go into a lot of the details about the parameters, but there are actually certain aspects of this that are really telling you what you're after. What is the probability or the likelihood of subject I transitioning from state L to state K? Think of no asthma to asthma, for instance, right? And you keep going like that, and there are certain things that you focus on, covariate effects or the true parameters that you're interested in. And this is what we call emission probability. This is actually where you're capturing the misclassification, right? So what is making people or children tell us the untruths, basically, telling us the wrong story? And there are determinants of that. It could be socioeconomic status, it could be educational status, it could be time lapse. Knowing that actually by itself is scientifically important, right? So that's basically what this emission probability is capturing. So the probability of misclassifying the subject state from N to M or from L to M, whatever you call it, right? So that's essentially, the other aspect of it. So what we have added is essentially, a second model that tries to tell us about the misclassification, but the first one, the transition one, is what's telling us, the inference about the true state, which is what we are after, right? So that's kind of essentially the contribution of this paper. So it basically, protects us from making mistakes and from misleading and reaching wrong conclusions, right? By using the right modeling approach, okay? So here we did some simulation study, and we showed in what situation can we just do the simple thing, and in what situations can we really have to be careful and try to guard against misclassification and so forth. So this is, again, set up that I'm not going to go too much detail about. This is essentially the findings that you need to do the right thing when you have severe misclassification, because otherwise you will end up with bad results. So therefore with wrong conclusions. This one I'm going to pass on, another paper that we wrote. Remember what I told you? What we're after is the underlying respiratory health of the child, right? But you're getting multiple lung function measures. You're getting information about asthma. You're getting information about chronic cough, about bronchitis and so on and so forth. But everything in collection or in totality is about the respiratory health of that child. So how do you synthesize across outcomes is basically essentially what this is after. And so we actually came up with a method that does that without going into a lot of details. Essentially, it allows us to do the right thing. So using this as examples, but also using standard methods that everyone uses all the time, there were a lot of findings from this study that were seminal and really moved the needle in terms of the science. And entities like the US EPA use this extensively in terms of setting policies, right? So very, very rich, very strong landmark study that benefited both from the scientific rigor of the domain science, but also benefited from the biostatistical advances as well that I told you about, just one or two examples of. Okay, now there were 5 cohorts, as I told you. The first cohort was recruited in 1997 or 94, something like that. The last cohort was recruited in 2005 or something. The state of California was monitoring these studies and many other findings. They were actually instituting policies. So the air quality was getting better and better over the long period of time. The benefit of this study is we had 5 successive cohorts that were done from the same studies, using the same study design, using the same instrument, and asking the same question. So we can actually see, as the air got cleaner, did we actually get benefit of it? Which is, these are millions and billions of dollars that are spent to clean the air. Did it make a difference? right? That's a very, very important question. And that's actually part of the children's health study. So as the air got cleaner, what happened? So what happened is actually, the economy grew, traffic was going up, population was growing, port activity in California was growing, and yet the air quality was improving. And so these two papers I'm going to show you briefly. One is a New England Journal paper that focused on lung development, and then it showed basically that the air pollution levels were actually going down in almost every measure in all the communities, especially in those communities that were high to begin with. Now remember, these were already low to begin with. They didn't show much improvement. But all these others basically came closer to the clean community, right? We still have a lot of variation, but not as big as this one, okay? And that basically, essentially, cohort C is the oldest cohort, 1904 to 98. Cohort E is a newer, 2007 to 2011. And then if you compare green and orange, this is basically population with low FEV % predicted. Then you can tell actually that there is a huge drop in terms of the compromised segment of the population. So this was a very, very important paper that got published in the New England Journal of Medicine. And another paper that I actually led, again, this is kind of, my bragging point, even though of course I'm more, proud of my statistical papers, but, as a statistician to publish in a JAMA is essentially tells you about the team science approach that we follow. In fact, the previous paper, the first author is also a statistician at ESC. So we have a very integrated team science approach, and we truly believe in being part of the team science in a very meaningful way. So this one was focusing on bronchitic symptoms. Again, same story. The pollution levels in nitrogen dioxide, particulate matter are all going down. Ozone didn't make much difference. Sometimes it even went up, but it wasn't consequential to begin with anyways. But all the other pollutants were very, very significant in impairing children's health. And as they got better, then you actually see a lot of bronchitic symptoms decreased with lower levels of nitrogen dioxide, NPM10 and PM2.5. So actually the policies worked, right? And this was evidence that they actually worked. So that was very impactful and reassuring to see, right? So, and it had very, very strong policy implications. Okay, now I'm going to flip the story. With climate change, we're seeing a lot of wildfires in California, for instance. What if climate change is actually reversing the air quality improvement that we saw? What would happen, right? This story is still not being fully told, but just to give you an example, in 2003, there was a wildfire, a big one, as you can see from the satellite pictures here. And we were actually able to show that wildfires and the emission from them had strong impact on health. But of course, the intensity and frequency of wildfires is really going up in the Western United States, states. And, so again, the story of climate change remains to be seen. So this is just to whet your appetite in a way in terms of what would come from this, approach. Again, I'm not going to dwell a lot about it, but this is more recent work. So we did this, what we call accountability studies. Basically try to see what are the policy implications of policy, actions, in any given setting. And this is done for California, but people have done it from around the world. And what we did was actually we use a causal inference approach, which is another, set of area of, methodology that has gained traction of late. And essentially the story was the same. Again, I don't have that much time to go over it, but I'd be happy to talk to people. So we basically used a version of causal inference called the G-computation approach. And we basically showed, we played like what if mechanism, right? Natural course of things. Basically, you observe things and you show, as I have shown you from the New England Journal paper and the JAMA paper. But then, what if maintained cohort C levels? What all the policies were not done, air quality stayed as high as possible? What would be the effect? Or what would, if % reduction in air pollution, either set to hypothetical standards or to what the EPA did, okay? So this scenario actually allows us to play kind of a game in a way, because a lot of them are not, they are counterfactuals. They are not observed states, but the modeling approach allows you to see what would happen if this course of action happened or that course of action happened. So this is a very interesting area of research, both from methodology, but also application point of view. And again, I'm not going to go into a lot of details, but the point is, of course, policies work and the impacts are real. That's basically the bottom line story. So the same story here for the different pollutants. And of course, this is, it takes a village or a country in a way to do this work. These are all the people that have participated. And this is only a very small subset and a lot of the funding agencies that did that. And of course, more research and more results, kind of lead to more questions, which is actually good for us, right? I mean, that's why we do science. The questions never cease to exist, but we just have to ask the right questions, and we have to respond or answer the most consequential questions. So we have to focus on the important ones. So this is, again, just to, where my research was going in terms of machine learning tools for, exposure mixtures, multiple outcomes that go up in dimensions. Nowadays in our smartphones or small gadgets, we measure like hundreds and thousands of measurements. So the issue of 4 or 5 lung functions is a child's play compared to the thousands of biomarkers that we can actually collect. But how do we handle it? So that needs a lot of methodologic development, causal inference, measurement error, mechanistic and statistical modeling, and multi-omics, in many, many, iterations or in many, many kind of, phases, that actually lead to a lot of challenge, but at the same time, a lot of opportunities. Okay, and of course, we have to use all the data that we can get in a live course approach, either by piecing data together or collecting data, if we are lucky on the same population, which takes decades. It exists, but not much. So new directions never cease to exist, right? Which is what keeps us going, and this is essentially to reflect that. Okay, so focusing on impactful science and policy, proper design, conceptualization, and conduct of research. And as part of this, active involvement in review and policy panels is important. We really have to immerse not only as scientists, but really go beyond and really disseminate, translate, and have an impact. And I take this seriously, actually, and I serve on a lot of panels. Like in terms of research, NIH is, of course, the main driving force. Yes, EPA has funded a lot of research. Health Effects Institute is an institute that's funded 50% by EPA, 50% by industry. And the whole point is to be a very neutral arbiter of science. So both the industry and the government trust this, and they fund it. And I've been part of this actually for almost 30 years now, including part of my postdoctoral fellowship. And NSF, of course, is funding research, but also charting the research direction. In fact, next week, I'm going to be in DC to participate in a panel, a roundtable on climate and health statistical methods. So ASA is actually American Statistical Association is trying to chart the agenda for what statistical methodology is most important, right? So all this is going on, and we need to be at the table in order to make a difference, right? Review and oversight panels. HAI has many committees. I serve on the review committee and also on the Global Health Oversight Committee. And of late, I'll come back to this later, climate change actually has been funded through a number of centers on climate and health. There is also a research coordinating center that's funded for Boston University and Harvard. And in fact, I co-chair the scientific advisory committee of that. The whole point is in galvanizing and coordinating efforts on climate and health research in a way that's meaningful and impactful, in a way that's coordinated. And as I said, I work on global health, and this is actually a HIT center that works in South Africa, Zimbabwe, and Ivory Coast. And the project is basically integrating and harmonizing data from across Africa to answer the question about whether extreme heat compromise maternal and child health, for instance. And there is a lot of machine learning, a lot of data science issues because the data is messy, but has a lot of gaps, a lot of questions. How do you answer questions, when you cannot have clean data? And of course, policy impact, and the national academies is at the forefront of it. EPA also has a process of it. And of course, my global activities that I told you about a little bit, including both data science, but also environment and climate change as well. All right, so let me monitor time. How much time do I have so that I can budget? Ooh. Okay. All right, so let me tell you briefly. So this is a National Academies Committee, basically, that was formed a few years ago at the request of EPA, because a lot of new methods were coming and people were questioning what EPA was doing. So it charges the national academies, can you assess all the scientific state of the art and tell us whether we need to change the way we are doing things in terms of assessing the regulatory decisions, right? So this committee, as you can see, this is a membership, and the people that I highlighted in yellow are actually statisticians. So Liz Stewart, who is the current chair of Biostat at Johns Hopkins, was the committee co-chair along with an exposure expert. I was a member of it, and Ivan, Francesca Dominici from Harvard, and Richard Smith from UNC. These are all statisticians, along with other scientists, basically to try to see, whether, what we can tell, EPA. And the statement of task is essentially to reassess the way, science is being, assessed and synthesized. And maybe two things that I want to say without going into a lot of detail is, one is the concept causality itself actually has been really controversial, because causality by itself is very important to all of us, but causal inference is, a very direct way of doing, causality, but it's not the only way, right? But there was a lot of confusion, either from misunderstanding or from deliberate misunderstanding, So I think this is basically clearing the air. And then maybe one thing to highlight is we also had a full chapter on emerging methods on observational studies that would contribute to causal inference. In fact, I was the lead, on that chapter, and we basically assessed all the new methods that have been happening and how they can be incorporated into the, assessment that is done by EPA and by panels of scientists. That's all I want to say about this, because I only have 7 minutes, now maybe 5. But these are all the findings. This is public report, by the way. You can actually download it, and if you go on chapter 8 and read it, you will like, and the whole report, by the way. But chapter 8 itself is the one that I was focusing on to basically tell you about what the state of the art is in terms of statistical methodology, not only on causal inference, but also on many other things in exposure and things like that. I'm not going to go into a lot of detail. So what excites me these days, besides being a chair of a department, is this is a new study that actually on methodology, another one led by one of my junior colleagues, Linda Valeri at Columbia. So this is essentially looking at air pollution, complex environmental exposure, and at the end is actually this Alzheimer's disease and related dementia. But in between, a lot of things are happening. People could die, or there could be hypertension, CVD, many other things that are happening. So how do you do causal inference in this life course approach when a lot of things are happening in between, even though your final outcome is ADRD? Okay? And there is a competing risk issue. There is a censoring issue, many, many things that are happening. Can you do the right thing, in a setting that's really complex? So the whole grant is actually about that. And this is still ongoing. Actually, there are at least 3 or 4 papers that are ongoing on this one that I'm not going to talk a lot about. But this involves a lot of studies. Some of these studies might be familiar to some of you. The normative aging study, strong heart study, MESA, the multi-ethnic study of atherosclerosis or something like that, which has an environmental component. So these are kind of the setup. I'm going to skip this one. Again, this is a disciplinary team. And finally, I think maybe I have -1 minutes now. So I'll tell you a little bit about what's happening with climate, right? So we just got funded for a P20 grant, which we call Climate and Health Action and Research for Transformational Change. At Columbia, we have a Climate and Health Center, but also we have a whole climate school that covers the entire university, because climate is a multi-sectoral problem. So this one essentially deals with a lot of components. It's climate and health, but it has justice, environmental health, exposure assessment, engineering, toxicology, sociology, epi, statistics, data science, climate science, omics. It's really, really complex structure. And it has membership from all these components. And again, I'm not going to go through this, but this is essentially the tree with the roots, basically, how we conceptualize the chart, basically. The whole grant is basically about understanding aspects of this tree, but also trying to make a dent on specific, components. And the bottom line is actually that there are two projects focusing on, aging-related, mental health outcomes. One is mostly on toxicology. The other one is observational study. So these are the two components. And then, of course, the structure is that, it talks about research. It talks about, this is IDEA integrated data and exposure analytics core, which I lead. And then you have the community engagement core. And this whole thing is supposed to basically feed each other to advance climate and health research. So this is a project that just got, launched about a month ago. And I co-lead it with two other colleagues, Jeff Shaman and Kemor Zoglo, who is a contact PI. Okay, so why is climate change complex? Okay, so because it touches on a lot of things. We just talked about climate and health, but there are many, many other things going on. There are heat-related impact, vector-borne disease, and so on. But then at the bottom, I'll come back to this. At the bottom, you have food insecurity, food shortage, malnutrition, child stunting, hunger, conflict, water insecurity. All these are happening with climate change. And you cannot just look at climate and health in isolation. You have to look at all these things. But of course, you have to approach it in a very systematic way, right? So when it comes to climate and health, much more complex beyond the availability of data, when it comes, to what's important and what needs to be added. So many different, health impacts, which I'm not going to bore you with, but both short-term and long-term, that we really have to pay attention to. And they're not, again, existing in isolation. And of course, climate change, there is a complexity, multidimensionality, and especially in global setting, you have fragile systems with very little data that you really have to pay attention to. We need to consider both mitigation and adaptation. Oops. Okay. And then you have both direct and indirect impacts. And of course, heterogeneity in availability of data. There are severe data gaps, which comes to ethics and responsible use. I don't know what's going on. And then the forecasting and so on and so forth that are actually important. And of course, big data gives us opportunity, right? So, we are really inundated with a lot of data. There is massive data bonanza. You have a lot of satellite-based data. You have, ability to combine many sources, both ground level and satellite. And then we have the ability to combine from disparate sources, but data siloing and, field siloing by itself is actually very important that we have to move beyond. And of course, electronic health data record and open access to data is extremely important. So I think that's probably, this is the last one. That's just one example of climate and health research that we are doing as part of our global health research. I think this is the last slide of my talk. Okay, all right. So it's a whirlwind of, ideas. So I hope I haven't rushed into a lot of details, but I think you get the message in terms of kind of the process of research, but at the same time, both depths and breadths of the research.
So let's give another round of applause to thank Dr. Berhane.